Okay, it's my pleasure to introduce Ruth Charney. Say a few words that I saw in Wikipedia about her. Before I get to what I know about her, she's the Berenson Chair of Mathematics at Brandeis right now. She was the president of the Association for Women in Mathematics starting in 2013. She's won quite a few other things, but many of us know her. She was at OSU for a long time. She says starting in 1984, I would have guessed, what year did you start?
84.
Same year as Ruth?
Yeah, but I started as postdoc.
Yeah, I know that. She was more advanced than you. Okay, so she started in 1984 and stayed here until 2003. This was, during that time, it was a great pleasure for me to have been able to collaborate with her all during the 90s and before. And it was for me, it was a great period of time. We wrote 9 papers or so on art in groups and non-positively curved spaces, which I think we're both still working on. We're still working on those topics. And in general in geometric group theory. I guess I had a few other things written down here, but oh yeah. So I've known her for a lot longer than I've known her for about 10 years longer than that. We overlapped in graduate school. I first met her when she was a first-year student and I was a last-year student. And we had the same thesis advisor who neither of us admit to anymore. Okay, so Ruth Charney, and she's talking about a bridge from geometry to, the general topic is hyperbolicity and beyond, and today it's going to be a bridge from geometry to group theory.
Thank you, Mike. Well, thank you all very much, everybody who was involved in inviting me. This is really an honor and a treat, and it's especially a treat to see again all the people I spent years as colleagues with here, and a lot of new faces as well. So, all right, so yeah, Hyperbolicity and Beyond is sort of the title of, this is a 3-talk series, and that's sort of the overall title. I'll be telling you a little more about what I'm going to do in detail later. So this first talk is the bridge from geometry to group theory. So I want to give you an introduction to what is geometric group theory. I'll give you a sort of a flyover to understand what geometric group theory is about. So everybody studies most people study a little bit of algebraic topology at some point in graduate school. And in algebraic topology, you start out with a topological space, and you associate various groups to it, fundamental groups, homology groups, cohomology groups. And then you use the groups to tell you about the space. For example, you want to know if 2 topological spaces are homeomorphic. Well, if they're homeomorphic, they have to have the same group. So if the groups are different, they're not homeomorphic. So we're using the algebra to understand or encode characteristics of our topological spaces. So geometric group theory goes the other way. You start with a group you're trying to understand, or a class of groups you're trying to understand, and you try to associate some, in this case, metric space, not just a topological space, but a space with a metric, and use the geometry of the space to learn about the groups. So how do we associate it? Well, what we want to do is take our group and realize it as some kind of groups of symmetries of this geometric object. And then say, if I can think of the group as symmetries of my geometric object, then the geometry should be able to tell me something about the group I'm working with. Okay, so that's the basic idea. Okay, so Now, here's an outline of what I want to do for the next, in these series of 3 lectures. So today, as I said, is called The Bridge from Geometry to Group Theory, and really I'm going to tell you about some of the fundamental ideas in geometric group theory, then tell you a little bit about the history of the subject, and finally just mention towards the end some of the new directions the subject is now taking. All right? In my second lecture, I'm going to go into more detail about some of these ideas I introduced today, talk about what large-scale geometry is about, and in particular, apply that to the notion of hyperbolicity. And finally, in the last lecture, I'm going to tell you about some work I've been doing on some new directions in the field and where my own work fits into that. Okay, so that's just to let you know. I know most people only come to the first lecture, but you never know. So if you like the first lecture and want to learn more, that's what the second and third lecture will be about. Okay, so let's get started. All right, so groups. Everybody, I think everybody in this room is a mathematician, maybe. So you all know what a group is. Groups arise in many different ways. In all different areas of mathematics, groups show up in one form or another. All right, so think of your favorite group, any group. Come up with a group in your head and think, how would I describe this group to somebody else who didn't know what I was thinking of? I wanted to explain what group I was working with. All right, well, maybe your favorite group is some kind of matrix group, a general linear group, or orthogonal group, or something like that. Maybe you're a topologist and you really like working with fundamental groups of topological spaces. Okay, they're very interesting. Maybe it's an isomorphism group of some set, like a symmetric group, or maybe an isomorphism of some algebraic thing, like the automorphism group of a free group. But there are a lot of people think about those kind of groups. All right, so here's one more. If you like creating sort of strange groups of different types, you might do that using what's called a presentation, which I will give an example of in a minute. But basically, you give some generators for your group, so everything in the group can be written as products of these generators, and some relations that those products have to satisfy, okay? So that's an example. Maybe you came up with something else that wasn't on this list, but there are lots of different groups, and they arise in lots of different ways. So our goal in geometric group theory, or in this talk if you want, is to try and think about groups geometrically as symmetries of some geometric object. All right? Okay, so let's try it. All right, here's a group. This is a presentation, all right? What's a presentation? Let's remember it's a set of generators. So my group in this case has 2 generators, R and T. That means everything in the group can be written as products of R and T, or powers of R and T. That could be positive or negative powers of R and T. But I can get from any point in the group to any other by multiplying R's and T's together, or R inverses and T inverses. But there are certain relations that these generators satisfy. For example, if I multiply R times itself 6 times, I find myself back at the identity element. T times itself twice, I'm back at the identity element. And then there's this sort of strange one that R and T, well, kind of almost commute, but not quite. Right? RT is not quite TR. RT is TR inverse. All right? Okay, if you've never seen presentations before, then you might not recognize this group. On the other hand, if you have seen them, you probably do recognize this group. Here's another description of this same group. Right? This group can also be described as the group of symmetries of a hexagon. All right? What is R? R is the rotation, pi over 3 rotation, which clearly if I do it 6 times, I'm back to where I started. And T is flipping across that dotted line. It's a reflection. And if I do it twice, it's where it started. And a little simple exercise, you can check that if you rotate and then flip, it's the same as flipping and rotating in the other direction. Okay, that last equation. Okay? So, but the point is, presentations can be really useful and they allow us to manipulate things, but as far as getting sort of a big picture of the group, this geometric picture is a shall I say, for the sake of this talk, a better way of viewing this group. Okay? All right. So, however, I should say that most of the groups we work with in geometric group theory are infinite groups. I remember giving a talk on some geometric group theory once with Bronzalm in the audience and saying, well, as far as geometric group theorists are concerned, all finite groups are trivial, so we just don't even count those. So, as I'll explain later, any finite index subgroup of a group really behaves the same way. So a finite index subgroup of a finite group is the trivial group. So they're all trivial. Anyway, so our groups are almost everything we're interested in is infinite groups, and that generally means that these spaces that we're going to build, that they act as symmetries on, are also going to be big. They're going to be infinite. Okay. So here's the sort of canonical example. If we take the free group on two generators, so we have two generators, I'm calling them A and B, and no relations whatsoever. Any string of letters of A's and A inverses and B's and B inverses gives a different element of the group. So I have the free group on two generators. Then the canonical sort of picture of it is that it acts on a tree, an infinite tree. So you have to imagine this tree goes on forever. A will shift you to the right 1 unit, and B will shift you up. Well, if you look at this picture, you say, wait, that's not a symmetry. That doesn't preserve this picture. I can't really do that. All right, you need to use your imagination, because things that are infinitely big, we can only draw with sort of as perspective drawings, okay? So you need to imagine that every single edge in this tree is exactly the same length. I just can't draw it. So this is kind of a perspective drawing. You're standing in the middle, so the edges close to you look big, but when you look out towards this way, they look small, but they're not. They're really exactly the same size, all right? So you have to imagine that we have this infinite tree with these blue edges and these red edges, and every single edge is exactly the same length, all right? Then I can translate my tree to the right, I can translate my tree up, or I can do this multiple times, up, over, down, up, etc. And it's all, and all of those preserve the structure. They act as symmetries, okay? All right, so that's just an example of the sort of things that we play with, all right? These infinite structures with infinite groups. I'm going to just throw in one little condition. In this presentations where you have generators and relations, there are groups for which you need infinitely many generators. For today, everything is going to be finite. I'm just going to assume I'm only going to work with finite generated groups. Okay, so some of this stuff still works with infinite generated. We're not going to deal with that today. So just assume all of our groups are finitely generated. Okay. All right, so here's the questions we have to address to do the sort of things we want to do. So the first thing, so I'm given a group, and the first question is, can I always realize it as the symmetries of some geometric object? You give me some group, I don't care, a matrix group, a presentation, whatever. Can I always find an object on which it acts as these nice symmetries? The second question is, it turns out some kinds of geometric objects are more useful than others, so what kind of geometry is going to be useful for us? And then once we find such an action and a nice geometry, what can we learn about G from this? Okay, so that's what I want to give you a taste of in today's lecture. Okay. All right, let me introduce a little terminology before we try and answer these questions. So I've been talking about geometric objects. So what is a geometric object? Let's make that more precise. So by a geometric object, I mean something called a geodesic metric space. So a metric space, you all probably know what a metric space is. You just have a topological space, or just a set if you want, together with a distance function. We know we have some function that tells us how far apart any two points are. A geodesic metric space is one in which the distance is measured by the length of the shortest path between them. So there has to exist a shortest path. It doesn't have to be unique, by the way, but it has to exist. There has to exist the shortest path, and the distance has to be equal to the length of that path. Or another way of thinking about it is that the metric, well, actually, let me show you these examples first, and then I'll summarize it. Okay, so let's look at a couple of examples. Supposing x is just the unit circle in the plane. Well, there are a number of metrics I could put on this. One of them would just be to use the Euclidean metric. The distance being from x to y is the length of the line from x to y, the Euclidean metric, right? The problem is, if my space is the circle, I want the distance from x to y to be the shortest path in the circle from x to y. And there is no path of that length in the circle. So in order to get a geodesic metric, I need to measure the distance as being the arc length in the circle, because that's the shortest path. Everybody understand? Okay, so it's like, how far is it from here to Tokyo? Well, sorry, you don't get to travel through the center of the Earth. You have to go around. So our space that we're living on is the surface of the Earth. And so distance is measured, well, actually airplanes, but distance is measured on the surface of the Earth. Okay, so that's the point. So these are sometimes known as intrinsic metrics. It's the metric you can get by traveling inside your space. You don't get to fly over it or go through it, or you have to travel on your space. Okay, everybody got that? All right. So here's one more. Okay, this space is just the grid, the integer grid in the plane. All right. So my space consists of the grid, and so the distance from x to y is the how many let's say each thing is unit 1, so 1, 2, 3, 4, 5, 6, 7. So the distance would be 7. This, by the way, is called the taxi cab metric, right? You have to travel on the streets. You don't get to go through the center. That's the taxi cab metric. But notice I gave this illustration to point out the fact that there can be lots of geodesics between a given point. Geodesic is the shortest path. We just use the word geodesic, shortest path here. So notice that any 2 points can be connected by lots of different geodesics. All right? Okay, so that's what a geodesic metric space is, and those are the spaces we're going to want to work with. All right? That's what our geometric objects are. Here's another one. I'm going to come back to this, so let's talk about this one for a minute. A hyperbolic plane. Now, I don't know if everybody's done hyperbolic geometry before, but let's talk about the hyperbolic plane. So the hyperbolic plane there are many models. I'm using what's called the Poincare disk model here. So the points are the points in an open disk. All right. But the distances, once again, use your imagination. The way to understand the distance between 2 points in the hyperbolic plane is to imagine that every one of those triangles is exactly the same size. So once again, we've got this perspective problem. As we go out towards the outside, towards the edges, it looks like those triangles are getting smaller and smaller. They're not. They're all the same size, okay? So, for example, if I want to go from this red dot near the sort of way out near the boundary here to this other red dot way out near the boundary, well, again, if it was Euclidean space, we might take the straight line, but notice that by curving inward, we can cross a lot fewer triangles than by going along that straight line. So the geodesic will not be this line, it will do this. And in general, geodesics, unless with the exception of ones that go right through the center, in general, geodesics will always try to curve inward because that crosses less triangles. And in fact, it turns out that geodesics are arcs of circles which intersect the boundary orthogonally at right angles. So the geodesics are arcs of circles, okay? All right, so perspective. Everything's bigger on the end than it appears to you. Yeah, question? I'm sorry? This is just a disk, just a flat disk. It's a flat disk, but here's what it is. It's a flat disk made out of stretchy fabric, more material. And and in the center it's not stretched very much, but the closer I get to the outside, the more I've stretched it, so that by the time you get to the outside, it's not won't lie flat on a table anymore. It's been stretched so much, okay? But it started as a flat disk, but got stretched more and more as you get to the outside, okay? Does that help? Okay. Okay, so that's so we take the hyperbolic plane with the geodesic metric, which is given by these paths. All right. All right. So we have our group, and we want to find a geodesic metric space that the group acts on with some nice properties. So what are these properties? Well, for starters, so what is an action, by the way? An action, you've got this space and you've got this group. By an action, we mean that each group element gives a map from the space to its space, to itself. And if you take two group elements, G and H, then the action is the composite. You can do G times H and it composes. Okay, so we've got this action. Well, the first thing, obviously, I said we want to act as symmetries. Well, the formal word for symmetries is isometry. That's what we call that mathematically, is an isometry, meaning that it preserves distance. Whatever the two distances were, I get 2 points. Whatever the distances is, now I perform this action of some element g on it. It takes it to two new places. Maybe it flips them, maybe it rotates. Whatever it does, the two new points are the same distance that they were before I did this action. That's an isometry. Okay, that's good. All right. Turns out that's not quite enough. Okay, we definitely want that property, but that's not enough. And why is it not enough? Well, let's think of some really stupid action, like maybe G acts trivially on my space, meaning it acts, every element acts as the identity that moves nothing anywhere. Okay, that's an isometry. All right. So, but it's not going to tell us much about the G, about the group, if it acts trivially. If it just does nothing to your space, you're not going to learn anything from this group. So we need a little more than just that it's an isometry, all right? Okay, these are a little technical. Don't worry about the technicalities. I just want to introduce the word geometric action. Geometric actions are going to be ones that act in a way that's useful. So useful means by isometries, that's what we just talked about. It preserves the distance. The second is that the action is properly discontinuous. I don't care if you know what that means. The takeaway from this is that if you look at how much of the group can fix a single point, you discover at most finitely many elements fix a point. It's almost a free action. It may not be free, but it's not. You can't get the whole group fixing a point, for example, for an infinite group. All right. So not too many elements fix points. And the last one, the way it's usually phrased is that the X mod G is compact. Here's a better way of saying it. I like to think of it as G sees almost the whole space. So I take a point and I move it around by G, take the orbit by G. I look at all the places I can get to by acting elements of G. Then that almost covers the space. That is, every point in the space is within bounded distance of one of those orbit points. So there's not like huge parts of the space that are irrelevant to my group. All right, the group's kind of seeing almost the whole space. So this just says that the group, that the space sees the group and the group sees the space. That's what those two conditions are. Okay, so as I said, it doesn't matter about the technicalities of it. We're just going to I'm just going to be referring to geometric actions, which means actions that are nice, that behave well. Okay? All right. So what's next? Okay, so we had 3 questions. All right, I said 3 questions that we were going to try to address today. And the first one is, can we always do this? You give me some crazy group with maybe some crazy presentation, and can I necessarily even find a space that it acts on, has a nice action? And the answer to this is actually amazingly easy. There's something called the Cayley graph for the space. So the answer is yes, always, always, always. I am assuming my group is finitely generated, as always. Okay, so assuming it's finitely generated, I can always do this, and here it is. I'm going to construct the space for you. So it's a graph, and here's how we construct it. We start by picking a finite generating set for G. So S is some finite set, and we then define a graph as follows. The vertices are in one-to-one correspondence with the elements of G. So each vertex will be labeled by an element of G. All right. And the edges, well, I connect to, so here's my, an element of G, and here's another element of G, and I want to know whether to connect those vertices to each other. And the answer is I connect them with an edge if and only if they differ by a single generator S. If I can multiply by a single generator and get from G to H, right? Multiplication by a single generator. And we often, just to remind ourselves of this, write the S on top there, telling us that that's the thing that gets me between them, okay? All right, given any group with finite identity set, I can construct this thing, right? So I construct it, and now I make it into a geodesic metric space simply by declaring each edge to have length 1 and measuring the distance between any 2 points, right? You just measure the length of the shortest path that gets you from anything to anything. Yes? Okay. All right. So, and then the last thing is that the action satisfies those conditions of being geometric action. That's actually an easy exercise. I'm not going to, oh, what is the action, by the way? If I'm given an element of G, let's not call him G or H, let's call it A, some element A. I just left multiply each of these by A. So this becomes AG, and this becomes AH, and you can see that AG and AH still differ by a single generator S. So it's just left multiplication. It translates this picture around. All right, so it acts, it's distance preserving, and it's not hard to check that the action's geometric. It satisfies all the conditions we want it to satisfy. Okay, all right, so that's good. We have a nice positive answer to our first question, which is, can we always find a metric space? Oh, here's some examples. All right, so the first one, well, let's look at the one on the right. First one is the free group. That is the Cayley graph of the, you just simply start with calling that this guy, you call it the identity element, and this guy is called A, this guy is called A times B, et cetera, or maybe, yeah, et cetera. You could just label all those vertices by elements of the group. And notice that if you do A and then B, you don't get to the same place as if you do B and then A. Right, there are two different. AB is not equal to BA in the free group. On the other hand, if we took the free abelian group on A and B, then we would have something similar, but now when we go along A followed by B, we get the same thing as if we go along B followed by A, we end up at the same point. All right, so instead we get the grid, with A is moving us to the right and B is moving us up, but now we get, instead of a tree, we get a grid. All right, the last one, I called it D12 here. It's that symmetry group with the hexagon that I showed you before. All right, it turns out this is its Cayley graph. If we use R and T, we have R. If we go around R 6 times, we get back to where we started. The T's just flip. In fact, R rotates that picture and T flips it, and that is the Cayley graph right there. It's almost the picture of the hexagon, but it's a little more complicated. All right? Okay, so there are some examples of Cayley graphs. Sounds good, that's the good news, and now let's talk about the bad news, all right? So the bad news is, first, that I might have picked a different generating set, and if I picked a different generating set, I'd get a different picture, a different metric, and maybe that's a problem. Well, it turns out that's not actually a problem, and I'll talk more about that later. In fact, a lot of the my second lecture on large-scale geometry is going to be partly about the fact that it doesn't really matter which generating set we pick. We're all always going to get the same information. So problem number one is it turns out to be a minimal problem. You don't worry about that too much, but we will come back to it. Problem number two is a big problem. All right, I have some abstract group, and I'm trying to learn about this group and its properties, all right? So first, what am I going to do? I'm going to construct the Cayley graph. Well, that turns out to be difficult. There's a very famous problem called the word problem. And the word problem is the following. Given a finite presentation, so I'm given a set of generators and a set of relations for a group, is there an algorithm? Could I feed this information into a computer and ask it to tell me when some word, meaning some products of generators, you take some thing that's a product of generators and its inverses, and you say, is this the identity element in the group? All right? Well, let's rephrase that. Suppose I started the identity vertex in my Cayley graph, and I read off this word. So the word gives me a path. I go along S and along R, etc., right? So I read off this word, and asking whether this word is the identity in the group is exactly asking whether that path ends up back at the identity. In other words, when I trace along this thing, am I going to end up back at the identity, or am I going to end up somewhere else? All right? If I can't answer that question, how am I supposed to build the Cayley graph? Right? How am I supposed to construct this thing when I can't even tell whether something's a loop or not? All right? So that's a kind of important question. And, you know, it would be nice to have an algorithm. I could build a computer algorithm that would build this Cayley graph for me. Not only are those algorithms complicated and hard to find, sometimes they don't exist. All right? So Pyotr Novikov in 1955 was the first to come up with examples of this. There are groups for which no such algorithm exists. All right? So if you can't answer the most sort of simple question like that, how are you supposed to, the point is you have to know an awful lot about your group before you can build the K-graph. All right? So that's bad news. That's the bad news about K-graphs. Right? Okay, so what are we going to do? Well, luckily, a lot of groups come with nice spaces that they act on. We don't have to use the K-graphs. Sometimes we do use the K-graphs, but we often don't need to worry about the K-graph. So, for example, if you start with a fundamental group of some topological space, you could look for some nice metric on that space. So if you have a fundamental group of a topological space, it automatically acts on the universal cover. So if we could put some nice metric on this, that would be perfect. Because given any metric on the base space, it lifts to a metric on the universal covering space, which this group preserves, all right, in a nice way. It's going to be symmetries. All right, so that's one example. For example, if we take the fundamental group of any torus with at least two or more holes, then it turns out those surfaces can always be given nice metrics of Riemannian metrics of curvature -1. They can be given these what are called hyperbolic metrics, and when we lift them to the universal cover, we get the hyperbolic plane that we were talking about before. So those groups all act in a nice geometric way on the hyperbolic plane, and we don't need to construct their K-graphs to study them. Okay. All right. So we often use. It's nice to know it exists, that it always exists, but that's often not the thing we actually want to use. All right. Okay. All right, so now let's go to questions 2 and 3. So we answered question 1, do these always exist? Yes. All right, questions 2 and 3. What types of metric spaces are going to be useful in this study? And what is it that they can tell us about our group? Okay. All right, so now we're going to do a little history here. So let's go back to the early 1900s. There was no such thing as geometric group theory back then. But Max Dane was studying fundamental groups of hyperbolic surfaces, like I was just talking about. Okay, so or hyperbolic manifolds in general. And as I observed, these groups, by passing the universal cover, act on the hyperbolic plane. And he used the geometry of the hyperbolic plane to prove all kinds of interesting properties of these groups. For example, let's see, did I say this here? Oh yeah, just learned how to do those. Okay, for example, there's only one, I'm sorry. Maybe next time I'll do a whole bunch of them. All right, so he was studying groups acting on the hyperbolic plane, and one of the things, he proved a whole bunch of things, but one of the things he proved is that the word problem, oh dear. How do I get rid of this?
Oh, it's a good question. No, it's more.
No. Nope. Oh, no.
You just hit OK. What would that do?
Wait, I think this should do it.
That did something, yeah.
No. Oh, just hit OK. I guess so. You have to do with this. I'm going to do that.
Just do it on your laptop.
No, it's not on my laptop. It's on. Oh, I see. I see. It is on a different screen, probably.
Okay, that went away. I'll try Alt-Tab, see if you can find the.
Alt-Tab?
Yeah, because that'll scroll through the different processes you've opened.
Well, it looks like it's on Chrome, right? But if you want it
Does anybody want to help me on this? I'm not a.
to go.
Oh. And if you heal it
It's not doing anything, it's not doing any of the, I don't know the first thing about these things.
Oh.
It's not even up here. It's on another, it's on a different
Which, is it that?
screen. Yeah,
It looks like you're.
yeah, yeah, you could do that. Click that. Thank you. Sorry. That's all right, I was worried about the promise. Thank you. All right, okay, so we've got Dane looking at fundamental groups of hyperbolic surfaces, and one of the things he proved is that they do have solvable word problems. So remember, there's this question of whether you could find an algorithm to determine which words were trivial. Not only is there an algorithm, there's a linear time algorithm. So if I feed in a word of length n, that it takes linear, there's a linear function in n, which tells me how long it'll take to answer this question. That's pretty good, a really nice algorithm, all right? Okay, so that's, that was sort of preview. Now let's fast forward to 80 years later, to the work of Mikhail Gromov. What Gromov realized was that so the hyperbolic plane has a Riemannian metric, okay, of constant curvature minus 1. You know everything about the local geometry of it, the global geometry, you know, there's just a huge amount of information contained in a Riemannian metric. But what Gromov realized is that Dane didn't need all that information. All he needed was the fact that if you draw a triangle in a plane, you remember how those things curved inward? That they curve inward and make very thin, or as they're called, slim triangles. All right? He took this observation and introduced a vast generalization of Dane's work and showed that you could apply similar methods to much larger classes of groups than Dane had done. All right? And this was really the beginning of geometric group theory. All right? And it happened in the late 80s and early 90s. Mike Davis came back from a sabbatical year with this preprint by Gromov and said, we have to read this. And we started a seminar to work through it, and it was you know, the beginnings of geometric group theory. Really,
But did we ever read it?
no. Well, we did. No, you asked the wrong question. Did we ever understand it? And the answer is maybe now, but it took about, about 30 years to understand it. So anyway, we weren't the only ones trying to understand it. So it started a whole field. All right, so yeah. So yeah, there's the triangles. They're sort of thin. They want to curve inward. Okay, so let's go on. So what did Gromov, this was Gromov's version of what Dane did. He introduced a new kind of hyperbolicity, a more general notion of hyperbolicity, which was defined as follows. So you're given your geodesic metric space, and you draw a triangle in that space. So what do I mean by triangle? Just pick any 3 points and connect them by geodesics. They're not unique. Just pick a geodesic here, a geodesic here, a geodesic. So you have 3 geodesics that form a triangle. And we say that that triangle is delta slim if basically any point on one edge, say this bottom edge, for example, is contained in the delta neighborhood of one of the other 2 edges. It's never distance more than delta from one side or the other. All right, what I've drawn here is a delta neighborhood of this edge and a delta neighborhood of this edge, and that has to contain this edge. And same for the other 2, any edge I pick, all right? So that's delta slim. We can get from any point on any edge to one of the other edges in distance at most delta. All right? And then you say that the space x is hyperbolic, or delta hyperbolic if you want to specify delta, but you say it's hyperbolic if there exists a delta such that every triangle in x is delta hyperbolic. Every triangle, for no matter where I start from, is delta hyperbolic. All right? And it turns out this is true in the hyperbolic plane. You can let your points go as far out to infinity as you want, and there's still this number, I forget, it's log something. I can't know exactly what it is. There's this delta for which will bound how big we're trying to get. All right? Okay, so some examples. let's take our tree. This is an infinite tree, just imagine. And take 3 points on the tree and connect them with geodesics, the shortest paths. Right? That triangle looks pretty thin. In fact, it's kind of collapsed into a tripod. So how far is it from a point on one side to a point on some other side? Well, this guy is zero slim. It's zero. It's distance zero from a point on any side to a point on the other side. Okay, so this is as slim as you can get. Delta is zero here. All right? Okay? And that's true for any 3 points I pick on there. All triangles degenerate totally into tripods. Right? All right. Let's try another one. Let's try the Euclidean plane. And I've drawn a series of 3 triangles there, but I can keep going, right? More right triangles, more right triangles. See those black dots on there? How far are they from one of the opposite sides? Well, it's pretty clear that as I make those triangles bigger and bigger, that those black dots get farther and farther and farther away from the other 2 sides. In other words, this is not hyperbolic. There's no way I can bound how far away a point gets from the other 2 sides. All right? So a tree is hyperbolic, a Euclidean plane isn't. So there are lots of spaces in which some triangles are thin and some aren't. Okay, so for example, if I take a tree cross a tree, a product of 2 trees, clearly if I draw a triangle that lives entirely in one direction inside the tree, it's going to be 0 hyperbolic. On the other hand, if I take a geodesic line in one tree, cross a geodesic line in the other tree, what I get is a plane. And in a plane, I can draw fat triangles, right? So yeah, there are some really thin triangles, and there are horrible big fat triangles. So no, it's not hyperbolic, because I can't bound them all. I have to be able to bound them all to get a hyperbolic space, okay? But you definitely get lots of spaces where there's a mixture, okay? All right. Oh yeah, so this is an introduction to tomorrow's lecture. I'm not going to say a lot about it today. I get to choose delta to be as big as I want. If I want to say my space X is delta, it is hyperbolic, okay, I'm going to choose delta to be 100 miles, all right? Well, if I choose delta to be 100 miles, at any triangle whatsoever I could draw inside this room is delta hyperbolic, yes? So the point is that this property says nothing, nothing, nothing about the local geometry, the up-close geometry, unlike, say, Riemannian geometry, which says a lot about the local geometry. This says nothing about local geometry. This says only something about what I refer to here as large-scale geometry. And large-scale geometry plays a really important role in geometric group theory. For example, it turns out that any 2 Cayley graphs, said Cayley graphs, you know, they're changed to generating, say you get a different Cayley graph. It's okay, they have the same large-scale geometry, which is what we care about, okay? So my second lecture is going to be a lot about large-scale geometry and what role it plays and more details on that, okay? So you will see more of that if you show up tomorrow. All right, so, okay. All right, so the whole point was now that we were looking for nice metric properties which told us something about the groups that act on, all right? So Gromov introduces this notion of hyperbolicity, and we have groups that are and groups that aren't, but we have a group that acts in a nice geometric way on a hyperbolic space. What can we conclude? I didn't actually define hyperbolic group. Sorry about that. The hyperbolic group is one that acts geometrically on a hyperbolic metric space. All right. So, yeah, let's just say that. Okay. So supposing we have this nice action on a hyperbolic metric space, what do we learn about the group? So I'm just going to give you a list of a few nice properties that come out of this. It turns out G is not only finitely generated, but it's finitely presented, because often even for a finitely generated group, you might need infinitely many relators, equations, all right, but not in the case of a hyperbolic group. G has a linear time solution to the word problem. Guess what? Dane's argument works in this generality. More or less the same argument works to show this, all right? It has finitely many conjugacy classes of finite subgroups. In particular, there's a bound on how the order of the finite subgroups, all right? Because there are only finitely many different types of finite subgroups. The centralizer of any infinite order element is virtually cyclic. That means it contains Z as a finite index subgroup. Maybe a better way to say this, or an implication of this, is that the hyperbolic group cannot contain a Z cross Z, a Z2, because then an element would have a centralizer that wasn't cyclic, all right? So it can't contain any Z2 subgroups. And for the rest of them, so here's some more, but now I have to throw out the virtually cyclic case. Assume that G itself is not virtually cyclic, but is hyperbolic. Then we also get that G contains a copy of a free group on two generators. It has what's called exponential growth, if you have ever encountered that. And it has uncountably many non-isomorphic quotients, and I could keep going and keep going, okay? The interesting thing about this, I don't have time today to prove any of them. The important point is we started with this simple well, maybe it's not simple, but this large-scale geometric fact that triangles were thin, and out came all this algebra. All right, pretty amazing, really. It's pretty amazing. All right. Okay, so let's move on. Here's what I'm not going to talk about, but is something that I've worked on a lot, and Mike Davis has worked on, and Jim Min has worked on, and a lot of people in this room work on, is some other notions. So hyperbolicity is just one example of a nice geometric problem. So remember, one of our questions was, what kinds of geometries are useful? Well, I hope I just convinced you that being hyperbolic is useful. All right? There are a lot of other useful ones. For example, we think of hyperbolic as being an analog, a large-scale analog of negative curvature. Well, there's an analog of non-positive curvature called the cat zero condition, which has also been extremely, extremely important. So groups acting geometrically on cat zero spaces, you can also give a long list of amazing properties that they satisfy. And there are a lot more groups that act on cat zero spaces. So certain three-manifold groups, Coxer groups, certain Artin groups. There are all kinds of interesting groups that act on these spaces, and these spaces have produced a lot of interesting information about those. However, I don't have time to do that. So I love cat zero geometry if anybody wants to talk to me about it, but I'm not going to do it today. We've got several experts here in the department on that. So. All right, so that's for some other time. Okay, so now I probably will end a little bit early. So I want to take the rest of the last part of the talk and tell you a little about some more recent work. So Gromov, as I said, came up with this hyperbolicity idea back in the early 90s, late 80s, early 90s, and people have been working with it ever since. I mean, people are still doing work on hyperbolic. But now, what's happening a lot, one of the directions of going on in the field is to try to make some of these techniques work even more generally. So I said, for example, that any group that contains a Z cross Z subgroup can't be hyperbolic. Oops, there goes, a large percentage of the groups we care about. So is there any way to make some of these techniques work in more generality? All right, how can we do that? And that's what a lot of people are working on. And there's really two directions of interesting work that are going on, both of which I think are producing really interesting results. So what we were talking about so far with Gromov's work is the case where we started with G, and it was acting geometrically on a hyperbolic space. That was our hyperbolic group idea, okay? That's what we worked with. Well, there's really sort of two ways we could loosen this up. One would be to loosen up those technical conditions about the action, about only finitely many elements fix a point, and it's co-compact, and all that stuff. There were these technical conditions. So one way would be to say, well, maybe we don't need anything quite that strong. Maybe we can loosen those up. And there's a lot of interesting work on this. So for example, there's a whole new class of groups called acylindrically hyperbolic groups, which is groups which act on a hyperbolic metric space, but the action's not geometric. It satisfies some somewhat weaker conditions. And it turns out there are lots of groups which are acylindrically hyperbolic, but not hyperbolic, and you can still get at least some of the same kinds of results, or use some of the same kinds of techniques to approach this. So I think that's a really interesting direction. However, the direction I'm going to talk about in my third lecture, and the direction I've been working on, is this one. And in this one, I still have a nice geometric action on a nice geodesic metric space, but it's only partially hyperbolic. Well, what does that mean? Well, remember we said there might be some triangles that are slim and some triangles that aren't. Well, maybe we could sort of pick out the good stuff and ignore the other stuff and still be able to do some of the kind of work we did. So, yeah, so here's what I'm going to, that's going to be the subject of my third lecture. So what I'm going to talk about is this. So there are many spaces that exhibit some hyperbolic behavior. And the goal of what I've been working on and what I'm going to tell you about in lecture 3 is to sort of capture which directions are good ones and which are bad ones, and encode the good ones in something I call a boundary, in a boundary. So we want to, let's go back to that. Hold on, I'll do this in a second. So yeah, so the idea is to say we've got some parts of this space that look hyperbolic, or some directions in this space that look hyperbolic, and maybe we could use them to learn about the space by ignoring the other stuff, or just collapsing it out, or not looking at it, all right? So that's the goal, so let me give you an example. All right, so I'm going to start with, first let me take the space X, which is simply a torus with a circle glued onto it at one point, the wedge of a circle and a torus. And the group involved is actually the fundamental group of that, but I'm not so worried about the group for the moment. Let's just worry about the space. Let's just think about the space, all right? I want to pass to the universal cover of that space. So what's the universal cover? Well, the universal cover of the torus is just a flat plane. It just wraps itself around the torus over and over. So it's just a plane. And the universal cover of a circle is just a line, just a real line, all right? But if I have the wedge product of a circle and a line, then on this plane, every time I hit, let's say an integer point, every time I hit a copy of this gluing point, a line pops out of it, all right? And then every time I go 1 unit along the line, it hits the plane again, all right? So I get a whole, what I call a tree of, I call them flats, but of planes. I get tons and tons of copies of these planes, and tons at each lattice point. I get an edge coming out, and at the end of that edge is a new plane. All right, and these planes don't intersect each other. I'm making a tree of planes. Okay, so you see that? Okay, that's the universal covering space. All right, let's think about what triangles in this tree of flats looks like. All right. Well, if I just stay inside a plane and take my 3 points to be in a plane, I can make my triangle as fat and horrible as I want. All right, sorry, fat is not horrible. It's from the point of view of hyperbolicity, it is. So okay, so I can pick my 3 points and make any kind of big, not slim triangle, right? So, all right. On the other hand, let's say I pick 2 points along one of these lines, one way down here, one way out here, and then maybe the other point's somewhere, who knows where, up here. So the on one side of the triangle is just my line, yeah? But now I want to get from over here to this point here. Well, I have to get back to this line somehow. So I'm just going to have to, make my way back till I get to the line and then go up it. But I'm going to have to do the same thing if I want to go down. I'm going to have to make my way back to that line and go down that line. And that triangle is going to be really thin. It might even be a tripod, So it turns out that things don't have to go straight up and down. If they mostly go up and down, if I don't let them stay in a flat for too long, but okay, maybe for a little while it goes over, and then it goes up, and then a little while it goes over, and then it goes up. And as long as I don't let it stay in any one of those flats for too long, the triangles are going to be boundedly thin. They're slim. I'm going to have a delta slim triangle. And the delta is only going to depend on how long I let it stay stay inside a flat. So as long as I bound how long it stays in flats, I have a delta that works. All right, so I've got lots and lots of delta slim triangles. And if I stick to those, if I can make my arguments based on those, then it's going to act like hyperbolic space, okay? So that's the idea. And it turns out that what we do is talk about directions that are good. In this case, a good direction is one that doesn't stay in flats for too long. It stays a bounded amount of time in a given flat. So as long as I have a bound on how long it stays in a flat, that's a good direction for me. Any geodesic that goes off. And I encode, the idea is that we'll take sort of rays to infinity that have these nice properties and make a boundary out of them and then use it to do hyperbolic geometry on it. Okay, so that's, as I said, is a preview of what I'm going to, so my third talk is called Boundaries of Groups, and that's a preview of what I'm going to talk about. And it turns out this idea can be used for a very large class of groups to get new information. Okay, so that's more or less everything, and this is just a summary of sort of where we've been, at least with this hyperbolicity. So classically, hyperbolic geometry had to do with the hyperbolic plane, or n-dimensional analogs of it for in the end. So hyperbolic n space, which is, the point is that had to do with Riemannian geometry. And to have a Riemannian metric, you have to have a manifold. So this this hyperbolic geometry was very powerful from the beginning, but it only applied to Riemannian, to nice smooth manifolds with nice Riemannian metrics on them. And therefore, and of course it was very powerful not only as large-scale geometry, but also lots of information about local geometry. But it only applies to things like fundamental groups of nice manifolds, okay? So then we pass on to Gromov's work, and in Gromov's work, we generalized we don't need manifolds anymore. These mostly have trees and all kinds of stuff. You know, we don't need manifolds anymore. All we need is a geodesic metric space with some nice large-scale geometry. We don't care about what the local geometry is, okay? And that allows us to use similar methods for much more general groups, much more general. And now, finally, what I was just giving you a hint of in the last two slides is we want to take that even further and look at geodesic metric spaces with some hyperbolic behavior, all right? And see if we can generalize this even further than what Radó did. So that's the plan. And I would say lecture 2 is really going to talk more about sort of what is large-scale geometry and a little bit about how the proofs of some of those things go, and then lecture 3 will be about this. So, trying to sell my ads, future lectures. Okay, so that's your flyover of geometric group theory. So, thanks.